Okay, so let's begin. We were talking about a review of complex numbers, and one of the things we talked about in the last class was giving you why are complex numbers necessary. And I am, of course, not going to go into a lot of details. I'm going to let you read through the reference book and the background section on complex numbers. It has a historical note on how the complex numbers came about and why are they necessary, right? But very quickly, we said, Kiji, it's like if you're trying to solve a problem, if you're going from point A to point B, within both of which lie in country X, I mean, it has a longer route and it has a shorter route, but that shorter route may pass through another country, which is country Y, right? So similar to that in engineering, in many applications across engineering, what you're going to come across is that the problem resides in the real domain, the solution resides in the real domain as well. However, solving the problem in the real domain becomes difficult. I mean, is a longer route compared to if you can have a shortcut through country Y, which is imaginary numbers or complex numbers, that allows you an easier way out of solving exactly the same problem. So that's one of the primary reasons why we like complex numbers so much in engineering applications and in scientific applications as well. Okay, so um, um, today, I'm assuming all of you are familiar with complex numbers already from your high school, from your SSC core that you've already done. But nevertheless, I'm going to give you a quick review of what those are. So I'm going to start out with algebra of complex numbers. So complex numbers, as we know, they have a real part and an imaginary part, right? So if I can write the complex number as being equal to x times r plus j times x sub I, right? Where x sub r is a real part of it and xi is the imaginary part of it, okay? And these are the operations here. So if I say, Kiji, what is the real part of x? This is a notation that I'm going to use throughout the course, right? So the real part of x, if I want to, so if x is a complex number, the real part of x is going to be denoted by this notation that I've underlined. The imaginary part of x is going to be denoted by this notation that I've underlined. Um, okay, so give me a minute, please.
Okay, and so the complex number, because it has a real part and it has an imaginary part, we can visualize complex numbers in a two-dimensional space, right? So we can imagine this in a two-dimensional space where the x-axis is the real part. So this is the x-axis is going to denote the real component. The y-axis is going to denote the imaginary component. And this vector, which you can see in green, represents as complex number, right? So this is a vector starting at the origin, pointing towards the point in space, which corresponds to that complex number. The x-intercept is xr, and the y-intercept is xi, right? So complex numbers are very frequently visualized in two-dimensional spaces, okay? In a two-dimensional space, where the length of this vector is the magnitude of the complex number, which is, as you all know, this is what the expression is. I mean, it's just the length of that. This is through Pythagoras theorem. The absolute value of x is xr squared plus xi squared square root. And the angle theta that it makes with the positive x-axis is tan inverse xi over xr. Okay? I mean, very fundamental stuff, something we're all familiar with, hopefully. Okay? Now, can you write xr as a function of the absolute value of x and as a function of theta? Can somebody help me here? I mean, if I wanted to write x sub r as a function of the magnitude and the function of the as a function of the angle, so what would that be? Ji Usman Nadeem. Usman, can you hear me? Manur? Yeah, anybody? Ji Munim.
Hello?
Yeah, go ahead.
Can you reiterate the question?
The question is, what would xr be as a function of the magnitude of the complex number and the phase of the complex number? right? So here's the point. So if I know what this length is, if I know what this length is,
Sir?
yeah, who was this?
Sir Hamza, sir, sorry to interrupt you, sir.
Yeah,
I
yeah.
think so. If we assume that the magnitude of this complex function is r, then we can think that the real part is represented by r cos theta, where
Yeah.
theta is the phase shift.
Excellent. So that's what I was looking for, right? So, I mean, that's just from simple geometry, right? So if you look at this, uh, graphical representation here, so if this is the length, if this line is the length, right, and which is the absolute value of x, so this length of this vector is absolute value of x, what would this be? This would be the hypotenuse, which is x times cosine theta, right? And I know that that is xr, right? So therefore, the real part of a complex number is equal to the magnitude of that complex number times cosine of theta. Okay. Hamza, do you have a question, or did you have an answer to the previous question? Okay. So xi, what would that be there for?
Sir, x modulo sine theta.
Excellent, right? So the modulo of x, which is the absolute value of x, times sine theta. Okay, so this would be a fundamental relationship between the magnitudes, the angle, and the real component and the y component. Okay, all right. Then we need to talk about something called Euler's formula. So how many of you are familiar? I mean, you should all be familiar with Euler's formula. What is Euler's formula?
So e raised to power j theta is equal to
Is equal to?
theta plus sine j sine theta.
Excellent. So e raised to power j theta is equal to cosine theta plus j sine theta. I mean, something you would have studied perhaps in your high school, or at least in the SSC core curriculum. Anybody has any idea how you come about this, by the way? I mean, किस तरह derive होती है Euler's formula जो है?
Maclaurin series?
Yes, through Maclaurin series. Okay, and I'm not going to go through the proof. The proof is actually there in the background handout that I've actually uploaded on LMS. So you're welcome to go through that proof as well. Okay, so if e raised by j theta is cosine theta plus j sine theta, what I can then do is the following. I can say, okay, if x is equal to x sub r plus j times x sub I, and then I say, okay, this, because xr is nothing but the absolute value of x times cosine theta, and xi is nothing but absolute value of x times sine theta. What I can do next is I can just say, okay, this is actually equal to absolute value of x. I can just take it out as a common factor times cosine theta plus j sine theta. Right? And from here, just using the Euler's formula, what I have inside the brackets here is nothing but what? E raised to power j theta, right? So this is equal to absolute value of x times e raised to power j theta, right? Just a simple use of the Euler's identity or Euler's formula, right? And this is, of course, what kind of representation? I mean, there's a particular name for this kind of representation of complex numbers.
Sir, polar form?
Polar form. Excellent, right? So this is the polar form. So this would be the polar form, right? And this would be the rectangular form. And both are equivalent. Okay? So yeah. All right. So let me now ask you some question. I mean, now that we're done with the basics, so we're still doing the basics anyway. Let me try to quiz you here. Okay. So, all right. So some questions. And I explicitly talk about these because this is something that we're going to keep on doing over and over again. I mean, in the later part of the course. Okay. So the first one is, what do you think e raised to power j 2 pi should be equal to? Right. So what all I've done is I just replaced theta with 2 pi, and I've replaced the absolute value of x that with the equal with a 1. So what would this be equal to?
Sir, can I answer?
Yeah, Ji, go ahead, Manur.
Sir, cos 2 pi plus j sine 2 pi.
Excellent, right? So that's how you would say this is cosine 2 pi plus j sine 2 pi. All right. What is cosine 2 pi? Manur, just stay with me here. So what is cosine 2 pi?
Sir, it's 1.
1. And what's sine 2 pi?
0.
0, right? So therefore, this is equal to what? This is equal to 1. And it's 1 because this is 0. Right? So e raised to power j 2 pi is actually equal to 1. And this, I mean, the way we've seen this is through the Euler's identity. I mean, we just expanded e raised to power j theta, e raised to power j 2 pi using Euler's identity, and we find out that e raised to power j 2 pi is actually equal to 1. We can also take a graphical look to see that this is also equal to 1. This is just another interpretation that I'm giving you here. The other interpretation is, let me imagine e raised to power j 2 pi as a vector in the two-dimensional space where the x-axis is the real part, the y-axis is the imaginary part. And e raised to power j 2 pi, therefore, is a complex number from the polar coordinate system, which has a magnitude equal to 1. And what's the angle for that?
So 2 pi.
Which is 2 pi is 360 degrees, right? Which is 2 pi radians. So essentially what you're saying is कि एक vector hai, right? So your 2 pi, what that means is the angle completes an entire revolution, or the vector completes an entire revolution around a unit circle, which is a magnitude of 1. Okay? So this is the vector that we're talking about. This is the vector we're talking about, which resides once again on the x-axis. Starts on the x-axis, it completes an entire revolution, completes a revolution of 2 pi radians, which is 360 degrees, and then it's back on the x-axis again, right? If it's back on the x-axis again, because it's unit magnitude, this intercept must be equal to 1. And the imaginary part is, of course, equal to 0. And that's another interpretation why e raised to power j 2 pi is equal to 1, which actually comes about from the Euler's identity anyway, right? But another perspective, if you will. Okay? Is that clear? Now, let me ask you another question here. I mean, just extending on our discussions. This is, what is e raised to power j pi? What do you think that is equal to? And going by, I mean, we can do it two ways once again. Let's go by what Mahanur said. I mean, this using Euler's expansion, okay? So if I use Euler's expansion, Euler's identity, this is cosine pi plus j times sine pi. And what is this equal to?
-1.
This is equal to -1. Why? Because cosine pi is -1. And of course, sine pi, we know that's equal to 0, right? And if you look at the graphical representation of this, so if somebody can, okay, Asad Khalid, can you try to explain, I mean, the way I did that for 2 pi, right? E raised by j 2 pi. Can you try to explain why e raised by j pi is equal to 1 using a graphical interpretation here? Angles को use करते हुए. जी असद, go ahead.
सर वो एक वेक्टर है हमारे पास जिसका मैग्नीट्यूड 1 है.
Yeah.
और थीटा जो है वो 180 है, मतलब वो नेगेटिव x एक्सिस पे 1 हो जाएगा.
Exactly. So theta for that is what?
और उसका इमेजिनरी पार्ट.
Exactly. Excellent. Right. So the theta is 180 degrees. So you start from here. एक vector यहाँ से start हुआ था. You go about and complete half a revolution. So that the angle the vector makes with the positive x-axis is now 180 degrees, right? So the vector that you're actually looking at is this vector. And because it's on a unit circle, the magnitude is 1. This is the negative x-axis, which is -1. Okay, just a visual representation of what this was, right? And similarly, very quickly, what about e raised to power j pi by 2? What would this be?
J.
J, excellent, right? So this is cosine pi by 2 plus j sine pi by 2. And I know that cosine pi by 2 is 0, right? Because, I mean, cosine of 90 degrees is 0 and sine 90 degrees is 1. So therefore, this must be j. And you can, of course, come up with the graphical representation where this is nothing but, so this is the vector you're looking at, which makes an angle of 90 degrees. This is pi by 2, right? And this, of course, is pi, and this angle here is 2 pi. Okay, a graphical representation. And very quickly, e raised to power minus j pi by 2. What would that be? So this is cosine pi by 2 plus j sine minus pi by 2. So what is this equal to?
Minus j.
Minus j. Thank you, Manur. Thank you, Abdullah. Thank you, Hassan. Right? And you can, of course, come up with a graphical representation as well. So minus pi by 2, chale, let's do that, right? So graphically, minus pi by 2 ka matlab kya hai? Right? So minus pi by 2 means if this was a two-dimensional space, you're starting out here, and minus pi by 2 is this angle, right? So this is the angle we're talking about. This is minus pi by 2, and this is the height. This is -1. Okay? Apologies, this is not too clear. And this is minus pi by 2. Okay? All right. Okay. Now, an important point here is, so what is e raised to power j theta plus 2 pi? What do you think this is equal to? Where theta is any arbitrary angle. I mean, theta could be anything between 0 and 2 pi. But all I've done is there's an arbitrary angle theta, e raised by j theta, and then I've just added 2 pi on top of it. What do you think this would be equal to? Ji Manu.
Sir, cos theta plus 2 pi bracket close plus j sine theta plus 2 pi bracket close.
Yeah, so what would that turn out to be equal to? So
It
Danya,
would be the same thing. It
So
would be the
E
same
j
thing.
theta.
same thing. Okay. And the reason why it's the same thing is because cosine theta is exactly the same as cosine theta plus 2 pi. Right? So that's one interpretation. But I would
Evolution.
say, yeah, let me just expand this here. So this is e raised to power j theta times e raised to power j 2 pi. Isn't that true? Right?
Yes, sir.
But I know from what we've done up above that e raised by j 2 pi is nothing but 1. Right? So this is 1. So therefore, this is nothing but e raised by j theta. Right? So there's an inherent ambiguity here, or an inherent periodicity, if you will, of 2 pi somewhere down the line. I mean, what do I mean exactly by periodicity? We're going to talk about in a little while later as well. Like in angles we know for a fact that the theta is exactly the same as the angle theta plus 2 pi. And if you look at this graphically or visually, I mean, that's another way to understand this. Let's say there was some angle theta which resided here, right? So there was this some e raised by j theta. So this is e raised by j theta. E raised by j theta plus 2 pi is another vector which has an angle equal to theta plus 2 pi. So there's a theta and plus 2 pi here. but I know that 2 pi ka pura revolution complete karne ke baad, I am going to be back in exactly the same place that I started out at, right? Because of the fact that the angles are modulo 2 pi, right? The wraparound, the angles wraparound, okay? And therefore, e raised by j theta would turn out to be equal to the same as e raised by j theta plus 2 pi. And would this hold true for just 2 pi or anything else? Right? So what about e raised to power j theta minus 2 pi? What would this be equal to?
Yes, sir. It'll hold for all even multiples of pi.
For even multiples of pi, exactly, regardless of whether they're positive or they're negative. Okay? And the reason, once again, is if you're going 360 degrees clockwise, that's exactly the same as going 360 degrees anti-clockwise. Okay? Because you're back in the same place. आप घूम के इधर से जाएं या उधर से जाएं, you're going to be back at the same place again, right? And another way, if I were to do this algebraically, I'd say that this is e raised to power j theta times e raised to power minus j 2 pi. But e raised to power minus j 2 pi is nothing but e raised to power j 2 pi, because once again, you're back at the same place again. So this is nothing but 1, right? So this thing here is 1. And because of that, this is e raised to power j theta. And from here, what I can conclude is a very, very important conclusion that we're going to end up using at some point or the other, which is okay, e raised to power j theta is equal to e raised to power j theta plus, as somebody, I think Munim said this, that this is equal plus any even multiple of pi. And another one of the ways to saying that is the following. For any, so let's see. I mean, what does this equation, what condition does n have to satisfy for this condition to hold true? I mean, can n be any real number? All right, excellent, Asad. The same, exactly the same. Very nice. So Maz, it does not have to be an even number. It can be any integer because of the fact that I have a 2 here. Because of the fact I have a 2 here. Does that make sense? Maz, can you unmute yourself?
Yes, sir.
Okay, if I had a pi times n, then this would have held true only for n being an even number. But since I have a 2 pi n, regardless of what n is, as long as it's an integer, it's always going to be a multiple of 2 pi. Okay, I'm always going to be adding a multiple of 2 pi. Okay, so this holds
Yes,
true.
sir.
Right. This holds true for any integer n. Okay, so this is the fundamental result. Right, this is extremely important. Not too hard, right? Quite fundamental, but important. Okay. Any questions so far? Okay, so let me quickly discuss what conjugation is. So if I give you a complex number x, which has a real component x sub r and an imaginary component x sub I, what do I denote the conjugate by? Is the notation that we use, and I think you're going to be hopefully familiar with this, is this x star, right? X star denotes a conjugate of a complex number x. Okay, what is the definition of this? I mean, what is this equal to? Anybody?
Sir, can I answer?
Gigi, please go ahead.
XR minus JXI.
Good. XR minus JXI. Okay, so this is the definition of conjugation, where you, when you do that conjugation, is just the imaginary number is, imaginary part is a negative of what it was earlier. Okay, what about the polar form? So I'm gonna pick on people here just to make sure everybody is here. So okay, Hamza is raised his hand anyway. Ji Hamza.
जी सर, तो पोलर फॉर्म के अंदर आपका एक्सपोनेंट के अंदर j के साथ नेगेटिव साइन आ जाएगा.
Right. So if I were to write this in the polar form, this turns out to be equal to the absolute value, therefore stays the same. And this is, so let me clarify this here. So if the actual complex number had an absolute value equal to absolute value of x and a phase of plus theta, then the phase of the conjugate of that complex number is minus theta, right? So the absolute value does not change. It's just what that changes is the angle. I mean, it's that the angle is a negative of what it was. Why is that? Hamza?
जी सर, ये इसलिए होता है क्योंकि कॉन्जुगेट के अंदर अगर आप इसको विद रिस्पेक्ट टू रियल कॉम्प्लेक्स के इनके ग्राफ के ऊपर इंटरप्रिटेशन से आप इसे देखें तो सर आप इसको अक्रॉस एक्स एक्सिस आप इसको रिफ्लेक्ट कर देते हो. तो सर जब आप उसकी रिफ्लेक्शन करते हो तो वाई एक्सिस का जो साइन, जो इमेजिनरी पार्ट होता है सर, उसका साइन चेंज हो जाता है. तो इसीलिए आपका ये रिफ्लेक्ट होना चाहिए आपके जनरल फॉर्म में. तो आई थिंक सो इसी वजह से नेगेटिव आता है वहाँ पे.
Right. So what I'm trying to depict exactly what Hamza said, right? So if this was the original complex number, the conjugate of that complex number looks something like this, right? Which has the same real component as the original complex number, except that the imaginary component is a negative of what it was. So this is minus xi. And this angle here, therefore, is minus theta. And why? So as Hassan said, sine of minus x is the same as minus sine of x. So that's an odd function. What exactly is an odd function? We're going to talk about. So because sine of x is equal to sine of minus x, that's why. Okay, so this is conjugation. All right. And then if you go through the background material, so there powers of x. So let me just quickly verbally go through this. So let's say if there's a complex number x and I asked you to find out what the square of the complex number was. How would you do that? Musa?
Yes, sir.
You said the square of the complex number?
Yeah, so how do you square the complex number? I mean, is there an easy way of doing it?
Not sure. Can't you just multiply it by itself?
Yeah, so if you multiply by itself, I mean, that's okay. I mean, you can do it in the rectangular coordinate system. You will be able to get something. Yeah, the polar coordinate system, that's a lot easier when you're taking powers. Okay. So very quickly, for example, so powers jo hai, so if x equals xr plus j times xi, which is equal to x times e raised to power j theta, then x raised to power n is what? I mean, it's going to be much easier for me to just use the polar coordinate system. Okay. I mean, Hassan wrote something in the chat box and I want to pick on him because I just want to have the discussion here. So Hassan says that the square of the complex number is going to be the real part squared plus the imaginary part squared. Hassan, can you think about this for a bit and tell me why it's not true?
Yeah, I might have made a mistake. Yes.
Yeah. So what you're saying is if I multiply x with x conjugate, that's what you get.
Yes.
And I'm going to tell you in just a bit, but let me deal with x raised to power n first. So x raised to power n is a lot easier for me to handle in the polar coordinate system. So this is equal to x e raised to power j theta, and this is whole raised to power n, right? And therefore this is absolute value of x raised to power n times e raised to power j times n theta, right? So taking the powers is a lot easier in the rectangular in the polar coordinate system. Okay. And so coming back to the point that Hassan's point here. So let's say there was an exercise here and say, what is x times x conjugate equal to? Right? And for this as well, I would rather use the rectangular coordinate system. The polar coordinate system. Okay, because I know x is equal to x times e raised by j theta. And what about the conjugate of x? That is absolute value of x and e raised by minus j theta. Right? So this is x, this is x conjugate. If I multiply the two together, what I get is x absolute squared times e raised by j theta minus j theta, which is nothing but 0. This is e raised by 0, which is equal to 1. And therefore, all you have at the end is x absolute squared. And what is this equal to? This is xr squared plus xi squared. Right? So this is the answer to what I was just saying earlier, right? So this is why x times x conjugate equals the magnitude squared of the complex number. Okay. Now, finally, okay. So there's multiplication of complex numbers, division of complex numbers. Let me not go into those because that's I think pretty straightforward. We can have some exercises in the homework to discuss that. But in this class, what I want to discuss is something that you may or may not have come across. So what I want to talk about is the nth root of unity. And how complex numbers play a part there. All right, so who has heard of this term here, nth root of unity? किसने सुना है, किसने नहीं सुना? अच्छा, किसने नहीं सुना? So who has not heard of it? Okay. All right. So it's something that you may have come across. It's just a name perhaps that may not be familiar. So what if I ask you, yeah, there's an equation, right? And there's a square which is of the following form. So I say, determine the solution.
So what is unity? 1?
Yeah.
So it's 1 plus minus 1.
Nth root of unity means the following. So I mean, let me start out with a simple example first. Okay. Let me start out with a polynomial of degree 2. Then I'm going to move on to polynomial degree 4, and then I'm going to generalize it, right? So if I ask you, right, so starting with a simple example first, if I ask you that you need to determine the solution to the following equation, which is x squared is equal to 1, right? In other words, determine the values of x which satisfy x squared equals 1. In other words, what are the values of x such that when you square them, you get equal to 1, right? So
1 minus 1.
All right. So it's plus 1 and minus 1. So there are two unique solutions to this equation, right? The principal, so one of the solution is plus 1 and the other one is minus 1. So x equals plus 1. That's one solution, and minus 1 is another solution. Okay? Achha. So far, so good. What if I ask you to determine the solution to the following equation, which is x raised to power 4 equals 1? So when I say nth root of unity, this is what I've actually meant, right? So what is the fourth root of 1 or the fourth root of unity? Right?
Square root of minus 1.
Square root of minus 1. Is that the only solution?
Another 1.
Is that the only solution?
Minus square root of minus 1.
Usman, can you unmute yourself? How many solutions would you expect? So there's a polynomial of degree 4.
Yes, sir. I guess 4 solutions and minus 1.
Good.
Iota minus iota.
Yeah. And plus 1 and minus 1. ठीक है? How do you come about that? किसने पता चला आपको?
I remember from past, I guess.
Okay. Remember from, sorry, what?
Sorry?
कहाँ से, where do you remember this from?
I guess from FSC.
Okay. So anybody else who remembers anything, how you come about the solution? Why is the solution plus 1, minus 1, plus j and minus j? जी हमजा.
जी सर, आई एम नॉट एग्जैक्टली श्योर, लेकिन सर जितना मुझे लगता है आप इसका सर अगर आप एक बार अंडर रूट लें, यू विल गेट टू डिफरेंट आंसर. एक्स स्क्वायर इज इक्वल टू प्लस माइनस 1, एक्स स्क्वायर इज इक्वल टू 1 एंड एक्स स्क्वायर इज इक्वल टू माइनस 1. अगर आप इसका दोबारा सर एक बार इसको अंडर रूट करते हैं इन दोनों डिफरेंट सॉल्यूशंस को, तो सर आपके पास आंसर आता है प्लस माइनस 1. एक आंसर आपके पास आता है आयोटा और एक आंसर आपके पास आता है 1. तो इस तरह आई थिंक आंसर इस तरह ठीक है.
ओके, एक्सीलेंट, गुड. मुआज.
सर वो हमने जैसे क्यूब रूट ऑफ यूनिटी किया था, तो 1 को इस तरफ शिफ्ट कर देंगे तो वो x4 माइनस 1 बन जाएगा. तो उस तरफ x स्क्वायर का स्क्वायर माइनस 1 का स्क्वायर, इस तरह हमारे पास दो टर्म्स आ जाएंगी. और फिर जो फर्दर x स्क्वायर है उसे सॉल्व करेंगे तो फिर वो इमेजिनरी टर्म्स, इस तरह 4 सॉल्यूशंस आ जाएंगे.
Okay, good. So अब here's a sort of a little bit of a more complication that I would give you here. What if I had x raised to power 100 equals 1, and I ask you to find the solutions to this, and you need to find 100 solutions to that, right? So the solutions that you're mentioning, I mean, they would be applicable to a very, very specific scenario where the root is 4. What I want to give you the framework for is a generalized framework, I mean, which would apply to any n, right? Whether this was 4 or whether it was a 6 or 10 or 100 or 1000, I don't care. As long as this was an integer, I would want to give you that generalized framework which would allow you to determine the solution. And that's what I meant by the nth root of unity. Maz, you have a question, or was this from before?
No, sir, that was from before.
Okay. So let me start out with x raised to power 4 equals 1. In the sense, KG, let me just stick with x raised to power 4 equals 1 and extend some of the ideas that I just did in the beginning, right? Where I said e raised to power j 2 pi is equal to 1, but e raised to power j 4 pi is also equal to 1, but e raised to power j 6 pi is also equal to 1, and so on and so forth. Okay? That's a starting point that we're going to use here. So what I do is, so we know that e raised to power j 2 pi times k is equal to 1 for any integer k, right? इसमें तो कोई मसला नहीं किसी को.
नहीं sir.
Right. So Hassan, I'll talk to you about this later. I mean, the solution that you're saying is, I mean, you're gonna have to have an iterative thing there. I mean, पहले 50th निकालें, फिर 25th निकालें, right? And this is a much broader general framework, right? So I know that e raised to power j times 2 pi times any integer is equal to 1. And let me just do this. So let me just say that x raised to power 4 is equal to e raised to power j 2 pi k, right? Where k is any integer. And this implies that x is equal to e raised to power j 2 pi times k raised to power 1 by 4 for any integer k, right? And I can cycle through all integers k and see how many unique solutions do I get, right? And this would imply that x is equal to e raised to power j times 2 pi times k divided by 4. And let me simplify this for, a bit. So this is e raised to power j pi by 2 times k. And the important point here is for any integer k. Okay. So the question then is, okay, how many solutions do I get? I mean, if k is any integer, there should be infinitely many solutions, right? Isn't that true? I mean, if k can go from minus infinity to plus infinity. But the beauty here resides in the fact that the angle is modulo 2 pi, right? So for instance, if I plug in k equals 0, what is the solution that I get? So I would get, so the solution that I get is x equals e raised to power j times 0. And then, so that's one solution. So, okay, x is 0, x, the one solution is e raised to power j pi by 2 times 1, right? x2 is e raised to power j pi by 2 times 3, and x3 is e raised to power j pi by 2 times 3. I think I've made a mistake here. This is 2. Okay, what about x4? x4 is e raised to power j pi by 2 times 4, right? So let me just stop here. What is e raised to power j pi by 2 times 4? This is nothing but e raised to power j times 2 pi. But I know that that is what? That is nothing but 1, okay, which is equal to 1. And what is the solution? E raised to power j equals e raised to power j times 0 is that's equal to 1 as well, right? So the x0 solution is exactly the same as x4 solution, right? Similarly, अगर मैं k equals 5 plug in करता हूं, so that is e raised to power j pi by 2 times 5, which is 5 pi by 2, and 5 pi by 2 you'll find out is nothing but pi by 2 because of the fact that it's modulo 2 pi. So this is e raised to power j pi by 2 times e raised to power j 2 pi. So this is e raised to power j pi by 2, which is nothing but x1. So it turns out, okay, if I keep on cycling through k from 4 onwards to 5, 6, 7, 8, and so on and so forth, I'll actually be getting the same results, and I will be cycling through the same results, right? But the unique solutions are what? The unique solutions are the first 4 that I gave you, right? Which is equal to 1. What is this equal to? What is e raised by j pi by 2? E raised by j pi by 2 is j. What is e raised to power j pi by 2 times 2? That's nothing but e raised to power j pi. That's minus 1. So let me use another color here. So this solution is 1. This solution is j, as somebody said in the chat box. This solution is minus 1. And this solution is what? This is minus j. ठीक है? और ये जो solution है ये दोबारा से 1 आ जाता है. ये solution है ये 12 से j आ जाता है, and so on and so forth. Right? So the unique solutions are only 4. Which are plus 1, plus j, minus 1, and minus j. Right? And if I were to visualize these solutions in a 2-dimensional coordinate system, what do I get? Let's say 2-dimensional coordinate system है. ठीक है, ये solutions कहाँ पे reside करते हैं? So, जी Muaz, you wanted to say something?
Sorry, sir. Oh.
Okay, Hafsa. Yeah, excellent. So Abdullah has the right answer. Hafsa has the right answer. So you have all of these solutions are on the axis, either the x-axis or the y-axis. So there's a solution here. So there's a solution here, which is plus 1. There's a solution here that is there's a plus j. There's a solution here which is minus 1, and there's a solution here that is minus j. And it turns out that this is actually, if you really think about this, these are uniformly distributed on a unit circle. I mean, this does not look like a circle, but visualize, imagine that this is a circle. I mean, that's how I draw, right? So they're uniformly, the solutions are uniformly distributed on a unit circle, 4 of them on the uniform, on the unit circle. And you can of course verify that when you raise to the power 4 of any one of these 4 solutions, you'll of course get something equal to 1. Okay? Any questions here before I generalize this to the nth root of unity? Okay, so let us generalize. So generalize, what do I mean? What is the solution to x raised to power n equals 1, where n now is any integer, could be any integer. Okay, so I go about the same principle as I did in the beginning, which is kg 1. I know that this is equal to e raised to power j 2 pi times any integer k, right? So I have that x raised to power n is e raised to power j 2 times pi times any integer k. Okay, and this implies that x is e raised to power j 2 pi by n times k. Okay, for any integer k. So how many solutions, unique solutions, am I going to get? So if you start thinking about this, ye kya ho raha hai? Right? So what you're saying is, so Munim, Abdullah, what do you mean by n? N solutions. Okay. So there are n distinct solutions. And where are they going to reside, Abdullah?
Sir, on this unit circle?
On the unit circle. And how? How are they going to be distributed?
Sir, with the phase difference of pi by 2.
Pi by 2 or 2 pi by n?
2 pi by n, sir.
2 pi by n, right? Because we're doing this as a generalized. Your 4 ke liye pi by 2, I agree with you. I mean, when n equals 4, it would have been pi by 2. Spacing would have been pi by 2. And let's do this this general analysis for, let's say, for n equals 8. For n equals 8, right? You would have k equals 0. K equals 0 pe where is the solution you get? K equals 0 pe this is the solution you get. Okay? So, and you say that x is equal to e raised to power j 2 pi by 8 times k. So this is e raised to power j pi by 4 times k. And let me use a k here to indicate this is the kth solution. Okay? So each solution is displaced from the previous one by an angle of pi by 4. So this is the first solution. This is going to be the second solution, which is the displaced by pi by 4. This is another pi by 4, 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 and another pi by 4, you're back at 0. And therefore, all of the solutions after this are exactly the same. So there are 8 distinct solutions. ठीक है?
ये वाली बात रिपीट करते हैं जरा.
So कौन सी वाली बात? Repetition वाली?
जी सर.
You see, this is
मतलब
e raised to
ये 8 जो है n equal to 8 के लिए ये 8 solutions है ना?
Yeah, of course.
Okay.
Right, so this is the point. This solution is e raised by j pi by 4 times 0, which I know is 1. This solution here is e raised by j pi by 4 times 1. This solution is e raised by j pi by 4 times 2. This is e raised by j pi by 4 times 3. This is e raised by j pi by 4 times 4. And you can verify pi by 4 times 4 is pi, and this is e raised by j pi,
Yes,
which is
sir.
nothing but -1. Okay? And this is e raised
ठीक है
by
sir.
j pi by 4 times 5. This is e raised by j pi by 4 times 6. This is e raised by j pi by 4 times 7. And when you get e raised by j pi by 4 times 8, if I just look at this a little bit closely, this is e raised by j times 2 pi,
2 pi.
which is actually nothing but this point here. वापस
Yes.
जो x axis पे था. तो इसके बाद मैं k और जितना बढ़ाता जाऊं, I'm going to be actually cycling through the same solutions over and over again. So the distinct
Okay, sir.
solutions that I get are just 8 in number,
Okay.
spaced equally on the unit circle. Okay? So the distinct solutions, so this is an important point here. So let me box this. So the n distinct solutions to x raised to power n equals 1 are given by e raised to power j 2 pi divided by n times k for k equals 0, 1, all the way up to where? कहाँ तक k जाएगा? All the way up to n minus 1. And because when it becomes equal to n, this is once again 2 pi. Okay? Any questions here? So this is going to wrap up my review of complex numbers. Okay? So I'm going to, so a few seconds for you to ask away any confusions you may have. Okay. All right. So I'm going to stop here with, with regards as far as the review of complex numbers is concerned, right? And I'm going to jump to the next topic, which is so if you can see on your screen, so this is a notebook that I'm going to share hopefully by tonight, and I'm going to upload these PDFs as well on LMS. But I want you to take a look at this. I don't know if you can see my pointer. No. Okay. So the section is continuous time signals. Okay. So that's a new section, that the new module that we're starting out with, right? So we're done with the course review, course overview. We're done with the review of complex numbers. And then we're starting out a new module, which is on continuous time signals. Okay. And within that continuous time signals, so let's me do first of all an introduction to what continuous time signals are. Okay. So who can remind me what is a broad definition, or roughly speaking, broadly speaking, of signals? Kya khayal hai? Any volunteers? Other than who've been speaking, there are a few people who've been engaged.
So it's like a waveform.
Like a waveform. G. Essen?
Something carrying information about something, about a physical property.
Okay, about a physical phenomena. And let's add on top of it, as a function of an independent
variable.
Excellent, right? So a signal is, broadly speaking, very roughly speaking, is a function of an independent variable which conveys information about some physical phenomena. Okay? Now, that's broadly speaking the definition of what a signal is. Now, within that signal, the module that we're talking about here is called continuous time signals, right? So when I use the keyword continuous, right, what comes to your mind immediately? I mean, what do I mean by continuous? Ji Asmir.
Continuous means that, okay, first of all, time is the independent variable.
Yeah.
So the function would exist on all values of time.
Okay. All values. So when you say all values, uska thoda sa expand kar dein. All values se kya murad hai?
मतलब any any division that you can have of time, like it will exist there. There is nowhere where the function is discontinuous.
Okay, good. So broadly speaking, for continuous time signals, the independent variable is continuous. And what that means is that the signal is defined for a continuum of values of the independent variable. Okay, so that's what I meant by, or when I use a keyword continuous time, I mean that the independent variable is time, and that independent variable is continuous. Therefore, the function or the signal is defined for a continuum of values of the independent variable, which is time. Okay, so for continuous time signals, the independent variable is continuous. So that's what differentiates it from another class of signal that we're going to talk about later. Independent variable is continuous. And the signal is defined for a continuum of values of the independent variable. So as a very, very quick, simple example. So, I mean, this could be a continuous time signal where the x-axis is time, right? And the y-axis is the signal we're talking about. And I'm going to use notation, for example, v of t to denote a voltage signal that you're measuring, for example, through an oscilloscope. Okay? Or the continuous temperature measurement that you're making as a function of time, which is continuous. And this wave or this signal is going to be a continuous signal, right? So that may look, for example, something like a sine wave or a shifted sine wave, right? So this could be a v of t. So this is a continuous time signal. Okay. And one of the important point I want to make here is, okay, I mean, remember at the beginning of in the review, the overview section, or overview lecture, I said, okay, signal is anything which conveys meaningful information about anything as a function of any independent variable, right? So that independent variable is not always necessarily time, right? It could be space, it could be anything that you can think of. I mean, it could be any other independent variable. Okay? It does not necessarily have to be restricted to time. However, for our notational convenience, for the rest of the course, I am going to use, and the book is going to use the term time to refer to the independent variable, regardless of whether it refers to actual physical time or not. Okay? And that's just a mathematical abstraction, once again, that we're talking about, right? That would help us in unifying the framework. Iske baad jab bhi main time ki baat karunga, right? Whenever I say time, when I say continuous time, I just mean that there's the independent variable is continuous, and I'm going to refer to the independent variable as time always, right? It may not necessarily be physical time. Is that point clear? Munim.
Sir, could you just go over the definition of signals as well as the significance of time you just told us?
Right. So, so we talked about a review or an overview of what a signal is, right? A signal is anything which conveys information about a physical phenomena. And we talked about several examples of signals that you could come across. The simplest of one could be is for example, I give you an electrical circuit, and I ask you to measure the voltage at a particular point in the circuit, right? Using an oscilloscope. And the waveform that you see on a scope is actually a signal, because it gives you how this behaves as a function of time, how the waveform behaves as a function of time. Okay? And
Yes,
so on and so forth. I mean, the other example, for example, I gave you, okay, how does the signal strength or the signal amplitude of the radio waves vary as a function of distance from the base station, okay, as you move out radially outwards, right? That, and if you were to plot that out, the signal strength as a function of the distance, that would be a signal as well, where the independent variable was what? The independent variable was time. Okay?
all right.
There was a speed as a function of time. जब car move कर रही है, ठीक है? I go from Islamabad to Lahore, right? And I just plot out what my car speed was as a function of time all the way from the start to the end, and that's going to give me a waveform, a curve, where the x-axis is time and the y-axis is the speed. That curve or that function, I'm going to say that's a signal, and that's a continuous time signal.
So for all intents and purposes, our independent variable will only be time.
So for all intents and purposes, our independent variable for practical purposes could be anything, but I am going to refer that to as time, even though it may not be actual time.
All right. Okay.
That's just a notational convenience or for expositional clarity. ठीक है, चीजें
For easier interpretation.
आप जो है उसको abstract level पे ले जाते हैं, ठीक है, so that अगर मैं ये कहना शुरू कर दूं ना कि यार इंडिपेंडेंट वेरिएबल जब टाइम आएगा तो मैं कुछ और बात करूंगा, जब कोई डिस्टेंस आएगा तो मैं कुछ और बात करूंगा, कोई और चीज आएगी तो मैं कोई और बात करूंगा, दैट विल क्रिएट अ लॉट ऑफ confusion, right? So the unified framework में I'm just going to use the notation or label or a definition time. ठीक है? It's just a label. The independent variable, I'm going to say time. Okay? Right. So, and that's the important point. And that's just for convenience, by the way. So for convenience, we will refer to the independent variable as time. Right. So, I mean, I have this quotations here, right? Even though it may not be physical time. And why do we do this? By the way, I mean, I said, Kitty, the reason why we're doing this abstraction is to make sure that we come up with a unified mathematical framework, which is going to be applicable to any domain that we could think of later on. Okay? Right. So that's why this abstraction. Okay. Munim, do you have another question, or this was from before? All right. So the notation that we're going to use to represent a signal, represent a continuous time signal, is the following. So we're going to use this notation, x parenthesis and this here, right? So this is very, very similar to mathematics. We talked about function, right? F of x. I'm sure each and every one of you is familiar with f of x. That's a notation that everyone is familiar, right? Where when we say f of x, what does that mean? Tell me, let me ask you this. I mean, so when I say f of x, इसका क्या मतलब होता है? जी मोहम्मद.
Sir, function of x.
A function of x, and where x is the independent variable, right?
Yes, sir.
So you say, Kaji, x is on the x-axis. This is an independent variable, and on the y-axis, I just want to see how does the function vary as I vary x. So that's nothing but a waveform as well. That's nothing but a waveform. देखिए waveform हो सकती है, waveform थी, कोई भी हो सकती है, right? So if you really want to build a connection with what you're familiar with, this x of t is nothing but a function as well, right? So this is that function, if you will, right? And this is, instead of that x, we're now using t. So this is the independent variable now. And this is the label for the function. For the and we're just using signals here, right? So I mean, if you really want to do this, so आप ये कह सकते हैं कि हमारी language में, as in the EE310 language, I'm just going to use signals instead of functions. Okay? Does that make sense? The functions that you're familiar with from your maths background, in our language, we're just using signals to replace that. Okay, that's just a fancy EE310 language that we're using. Okay, and we're going to use these parentheses, right? So these parentheses represent that is a function of t. Okay, and just like f of x tha, you could maybe have g of x as well, right? Where g now represents here, g is another function, not the f function, but another function, right? So the g and f are actually labels of what that or names of that function. Similarly, x of t could be a signal, y of t could be another signal, v of t could be another signal, I of t could be another signal, and so on and so forth. But we're always going to have parentheses to indicate that whatever appears inside the parentheses, which is almost always going to be t, whatever appears inside the parentheses, that's what the independent variable is for the signal or for the function. Okay, is that clear? Okay. All right. So let me get rid of this. I just quickly want to introduce complex signals. I mean, very, very often, I mean, just like, if you go back to numbers, right? So you had real numbers, right? And you had real numbers, and then an extension of those real numbers were complex numbers, right? And we said complex numbers are needed because there are many, many engineering applications where you would need to jump from the country of real numbers to the country of complex numbers, okay, to ease your analysis, to solve your problems, right? Just like that, in the real world, you have real signals, right? But to solve engineering problem, you define something called complex signals as well, right? And if you've grasped the idea of complex numbers, then the idea of complex signals is not a whole lot different. Okay, it's just a simple extension of the ideas of complex numbers to complex signals. Okay, so here's how. So a complex signal, x of t, we can say is equal to the real signal plus j times the imaginary signal, right? So the only difference of this from the complex number that we were doing was कि अब यहाँ पे the real part has now become a function of time, right? So the real part therefore is a signal, and the imaginary part has become a function of time, a function of an independent variable, and therefore the imaginary part is a signal as well. The imaginary part is a function as well. Okay, because of which there's a complex signal now, right? It's just composed of two real signals. One is the real part, and the other one is the imaginary part. Okay. The next question is, why is this necessary? It turns out that there are many, many applications in, for example, radars, in communications, in circuits, in many, many scientific applications as well, in which your life becomes a lot easier if you define something called complex signals. Okay, and this is the definition of complex signals. Okay. Now, if I were to ask you to plot a complex signal, how would you plot it? I mean, complex numbers are in two-dimensional space, right? लेकिन अगर complex signal की मैं बात करूं तो I mean, how would you sketch this? How would you plot it? जी मसना?
सर आई थिंक जैसे कॉम्प्लेक्स नंबर्स प्लॉट करते हैं उसी तरह करेंगे.
Okay, but where does the time? So now you have a function of time as well, right? So what we have here is this is a function of time. And this itself is also a function of time.
Sir, 3D plot हो जाएगा x, y and z axis.
Okay.
लेकिन
Okay. There might be an easier way of saying this. Okay. What if I said, Katim, in order to completely specify this complex signal and the plot of it, so let me plot the real part separately and the imaginary part separately. I mean, would that work?
Yes.
Of course it would work.
Yes, sir.
Okay. So what I can do is, in order to, so then some application I would come across in signals as well. Signals course ke duran mein bhi, I mean, many of the times would actually be dealing with real signals, but sometimes would also come across complex signals. So in order to teach you the basics, the fundamentals, the abstract fundamentals. Okay. Ji Hamza.
सर हम इसको इस तरह भी नहीं कर सकते फॉर अ वेरी स्पेसिफिक टाइप ऑफ क्वेश्चन और लाइक प्रॉब्लम हम अपना टाइम फ्रेम फिक्स कर दें और उसके ऊपर सिंपल कॉम्प्लेक्स लाइक रियल कॉम्प्लेक्स डायग्राम बना दें जो आप नॉर्मल कॉम्प्लेक्स नंबर्स के लिए
But that would only be for one particular time.
जी.
Get it, Hamza? Right. So here's how I can explain it to you. Right. So let's say this is a complex signal in which this was the real part. This is xr of t, and this is xi of t. Right. So the complex signal is now composed of two real signals, the real part and the imaginary part. Let's say, hypothetically, this is what xr of t was. Okay, and say this is what xi of t was. Right? It turns out that if I just look at this signal for any particular time, at any particular time, let's say this is the time that I was looking at. Right? So at this particular time, this is the real part of the complex signal, and this is the imaginary part of that complex signal. And at this particular time, I can, of course, depict this in a two-dimensional space. Okay? Because it's at a particular time t, it's nothing but a complex number. Function भी तो यही होता है ना कि मैं किसी independent variable की कोई एक value पे देखूं, so then what I'll get is a number. Right? And I just want to see कि my independent variable, I keep on varying it all over the place, and I just want to see how the function varies. That's what the function is. That's the entire characterization of a function. And this is exactly the same here as well. So xr of t is this entire waveform as a function of t. Xi of t is this entire function waveform as a function of t. And then at a particular time t, let's say at 1 second, if you sample this at 1 second, the real part का कोई number आ जाएगा, imaginary part का एक number आ जाएगा, that combined together gives you a complex number. Okay, in a two-dimensional space. Is that clear, Hamza?
Yes, sir. Thank you.
Right? Now, at the same time, can I specify a polar representation of this complex number? What do you think? Can I do that? Is that possible?
Sir, polar representation of the function or?
Yeah, of the function.
Okay.
क्या ख्याल है? Yeah, Hassan, mod and theta. All right. So anybody else? Ji Hamza?
सर आई डोंट थिंक सो आप इसको विद रिस्पेक्ट टू पोलर कर सकते क्योंकि सर पोलर के अंदर आपके दो बेसिक कंपोनेंट्स होते हैं सर एक आपका मैग्नीट्यूड ऑफ द कॉम्प्लेक्स फंक्शन और सर फिर एक आपका एंगल सर मैग्नीट्यूड का कोई एज सच वो नहीं यूनिट नहीं होता अगर मैं उस सेंस में बात करूँ सर, थीटा भी एक लाइक रेडियंस वगैरह में डिफाइन होता है, उसको विद रिस्पेक्ट टू टाइम आप उसे नहीं लिख सकते। आई डोंट थिंक सो आप लाइक पोलर में उसको इस तरह कन्वर्ट कर सकते हो, जितना मुझे समझ आ रहा है अभी तक।
Okay, so what if I told you this? If I say, if I were to compute the magnitude of this, I would just say, okay, this is xr squared of t plus xi squared of t. I mean, can I say this? In other words, कि मैं अगर xr of t स्क्वायर करूं और xi of t को लूं, उसको स्क्वायर करूं, उन दोनों को ऐड कर दूं और फिर स्क्वायर रूट कर दूं, तो what do I get at the end of the day? What I get is another function of time, because essentially what I'm doing here is what I'm essentially doing is here, okay, at each and every particular time t, I'm squaring and adding and taking the square root, and I'm doing this for all continuum of values of the time t. So this is being done all over the place from minus infinity to plus infinity. ठीक है जी अहमद?
जी सर, मैं पूछ रहा था कि जो कंटिन्यूअस एक से हम कंटिन्यूअस होने के लिए क्या कहते हैं, उससे क्या मतलब इसके पीछे उसके कोई एंड पॉइंट्स नहीं चाहिए, मतलब कि इन्फिनिटी तक जाना चाहिए, इन्फिनिटी तक?
हाँ, so infinity तक जा रहा है, इस साथ I cannot depict that minus infinity to plus infinity on my tablet, ठीक है, or anywhere, ठीक है. So this is just a representation. Let's say this stops here. Yeah, that's still a valid representation.
तो फिर वो discontinuous हो जाएगा, discontinuous.
I mean, it's just a depiction. I mean, let's visualize कि जा रहा है minus infinity तक और plus infinity तक.
ठीक है.
Otherwise, this is just a depiction. Okay, my point once again was कि if I tell you कि यार अब given xi of t and given xr of t, why don't you plot for me this thing here, a function xr squared of t plus xi of squared of t whole square root, right? So Hamza, I mean, given these graphs, would you be able to do it?
Yes sir.
क्या होगा ना, वो हर टाइम के ऊपर I'm just actually
जी सर,
एक डायमेंशन एक्सटेंड करनी है ना, फंक्शंस यही तो होते हैं कि एक किसी
जी सर, मुझे समझ आ गया,
और वो टाइम के ऊपर एक्सटेंड कर दें, राइट? सो आई गेट सम वेवफॉर्म, राइट? सो दैट वेवफॉर्म कुड बी arbitrary, not exactly sure what it's going to turn out to be. Let's say something like this. We'll always stay positive because of the magnitude. Okay? So it turns out that the absolute of x of t is also a function of time. And the similar thing I can say about theta of t as well. So if I just say tan inverse xi of t divided by xr of t, and that will give me the phase, but as a function of time. If I fix xi of t and xr of t, for example, at t equals 1 second, I'm going to get a number of theta at 1 second. And I change this from 1 second to 1.1 second, I'm going to get another number at 1.1 second. And I just keep on varying t from minus infinity to plus infinity. And I just see what the behavior of theta of t is going to look like, given xr of t and given xi of t. Okay? So the phase is also a function of time. The magnitude is also a function of time. And therefore, the polar representation does exist. This is x of t times e raised to power j theta of t, right? Except all that's changed is that the magnitude is a function of time and the phase is a function of time, right? So this is a complex signal. All right. Any questions here? I'm going to stop here and take any questions that you may have.
तो सर ये आपने ब्लू वाला जो ग्राफ बनाया, ये एक दो बार रिपीट कर देंगे आप, किस तरह से आपने?
So ये वाला blue वाला graph is just an arbitrary waveform. जो I'm not exactly sure कि यही आएगा नहीं आएगा. All I've done is कि I've at each and every one of those times, मैंने यहाँ पे देखें ये किया, इस पे क्या होना चाहिए, इस पे ये जो वैल्यू आएगी ना इस जगह पे, वो क्या होनी चाहिए, this value squared plus this value squared and square root, right? And then I just do it for each and every one of the time on the x-axis. and I'm going to get some graph, and this is just
जी
one
सर
arbitrary depiction of the graph. जरूरी नहीं है कि exactly यही आए. ठीक है, it's just a depiction, Ibrahim.
ठीक है
ठीक है.
थैंक यू
Then what's important to just get that point across. Anybody else who has a question?
सर
Yeah.
सर जो हमने फाइनल ग्राफ हम प्लॉट करेंगे जिसमें इमेजिनरी और रियल पार्ट दोनों होगा, तो आप कह रहे हैं वो थ्री डायमेंशन में होगा?
नहीं, 3 डायमेंशन में करने के बजाय आप दो प्लॉट्स दे दें. यानी आप
नहीं सर,
you get a plot as a function of time of the phase, and you get a plot of the function of time of the magnitude. So there are two plots.
अच्छा, तो सर वैसे अगर इस तरह कर सकते हैं कि अगर कोई सॉफ्टवेयर है उस पे हम हमारी जो है इंडिपेंडेंट एक्सेस वो इंडिपेंडेंट नहीं मतलब रियल और इमेजिनरी एक्सेस का ग्राफ हो और वो एक टाइम वेरिंग होता जाए, मतलब जिस तरह टाइम चेंज होता जा रहा है उस तरह ग्राफ चेंज होता जाए.
हाँ, उसको फिर आपके दो एक्सेस चाहिए होंगे in any case.
ठीक है,
दो एक्सेस चाहिए होंगे, एक यानी दो प्लॉट्स चाहिए होंगे. in other words, कि एक आप you would have to depict यार how is the real part varying as a function of time. You would also have to depict how the imaginary part is varying as a function of time.
नहीं सर, लेकिन हमने पहले वो किया तो था कि इमेजिनरी एक्सेस भी थी और रियल एक्सेस भी थी एक ही ग्राफ पे, तो उस चीज को मैं कह रहा हूँ.
उसमें टाइम फिक्स था. ओके ओके गुड. सो व्हाट यू सेइंग इज कि कोई ऐसी चीज हो सकती है कि मैं 2 डायमेंशंस में ही उसको देख रहा हूँ लेकिन वो टाइम के साथ चेंज हो रहा हो. इज दैट व्हाट यू सेइंग? जी बिल्कुल हो सकता है, बिल्कुल हो सकता है, लेकिन इट्स जस्ट दैट कि जी वो इट विल नॉट गिव यू दैट एंटायर इंफॉर्मेशन. आई मीन हाउ वुड यू स्टोर दैट इंफॉर्मेशन? विजुअली शायद समझ आ जाए क्योंकि आपकी अपनी ब्रेन की मेमोरी है ना, आपको पता होगा यार वो पहले क्या हुआ था और अभी क्या हो रहा है.
जी.
Right? So we'll come back to this, Hamza. So it's an important point. Perhaps an example that we do when we talk about complex exponentials. So remind me and I'll talk about this more.
ठीक है सर.
Okay, so what you're saying is possible indeed. Lekin there's some loss in visual information when you do that.
ठीक है सर.
ठीक है.
Sir, can you explain again how you would make two plots from the polar version of a complex signal?
Okay, so you would have now, so here you would have a plot of the, as a function of time, you would have a plot of the magnitude. Oops, sorry. X of t, which is the magnitude. Okay, and it would be some arbitrary waveform. I mean, let's say hypothetically, this is what it looks like. I mean, it's always be positive. Okay, and then there's a phase. So, and that phase could perhaps look something like maybe constant, maybe decays, and maybe goes in the negative side. Okay, so now you're using two plots to depict that signal in two graphs. So what I can do is let me. So what I'm thinking is some examples in MATLAB with visual depictions. Okay, the real part, the imaginary part. What does the phase look like? What does the magnitude look like? And maybe I'll share those demonstrations with you on LMS. Okay?
Yes, thank you.